Alright, so in this video I'm going to go over how I got the first set of calculations completed for trial 1. So you'll notice in the data sheet given to you, and this is experiment 11, sorry, gas concepts, that the trial 1 is completely filled out and there are some equations there to help you complete the calculations for trial 2. So I'm just going to go through and show how I got the answers to fill in all the empty spaces that you need to fill in for trial 1, and then you can use the same methods to complete the table for trial 2. Make sure you are showing your calculations on the lab. There's a space at the very bottom because those are worth points as well. So this is what your table looks like. There are some empty spaces here and there. Some of the spaces that are filled in, you'll notice also need a conversion. Okay, so every space that has a blue equation by it, that's what you need to complete. You also have a percent error and an average percent error that's not fitting on this table here, so just be aware of that. All right, so let's start at the top. Okay, so we have the amount of magnesium that was used in the experiment. We have the temperature of the room. Now, whenever we use any of these equations, the combined gas law or the ideal gas law, we need the temperature to be in Kelvin. So we're going to convert that to Kelvin simply by adding 273 to the degrees Celsius. Okay, so Kelvin is equal to, in this case, we have 23 plus 273. And I know I'm not sticking with significant figures very well here. 23, so we get 296. So I'm going to fill that in. So whenever I use this, I'm going to use the 296 Kelvin version. And you'll notice I have T1 written after the room temperature, because this is going to be the value, this 296 is going to be the value that I'm going to plug in when I get down here for T1. Okay. So looking at the next two, so we have vapor pressure of water. Okay, well first off, let me explain why we have vapor pressure of water. If you watch the video of the experiment, what happened was you reacted magnesium with hydrochloric acid. And when that happens, you get H2 gas. And what we're trying to calculate is the pressure of that H2 gas. But when they put that tube in the water, the gas that they measured was not just H2 gas, there was a little bit of water vapor gas in there as well. So we need to subtract out that water vapor so that we have just the dry H2, which comes down here. Okay, so the reason we need the vapor pressure of water is because we're trying to get rid of that water vapor that was present in the top of that tube mixed in with that dry hydrogen. So this is just a value that you would get from a CRC book. So this is just the vapor pressure of water, so that's why it's filled in for you. Barometric pressure. So this value here, that is whatever the pressure was that day outside. So barometric pressure actually varies a little bit day by day. Ideal would be 1 ATM, but as you notice here, it was 1.005. Okay, in trial 2, it varied even a little bit from here. Okay, so this is the total pressure. So if you look back at the law of partial pressure, Dalton's law of partial pressures, to figure out the total pressure of the atmosphere around us, P sub T, we would need to add the partial pressures of all gases present. So that's how we're going to use this. We're going to take the total pressure of the atmosphere, and that total pressure is made up of water vapor and H2 gas. Okay, so we're trying to figure out what pressure the H2 gas was. So the equation we're using to figure that out is the law of partial pressures. So the total barometric pressure includes water vapor and H2 gas. So if we know the total barometric pressure, because we can look that up on Wonderground or any sort of weather app, and we know the partial pressure of water from finding it in a table or a book, we can calculate how much of that pressure that we collected, how much of that gas we collected was H2. Okay, so we're going to do that by taking PT, the total pressure, and subtracting out the partial pressure of water. Because when we subtract out the water, all that's left is going to be the pressure of the H2. Okay, so I'm going to fill in these values. The total pressure, total barometric pressure, is 1.005 ATM. I'm going to leave off the units because they're both in the same. We're going to subtract the partial pressure of water, 0.029. And when we do that, unfortunately I do not have my answers at hand, so let me calculate this quick. I get 0.976. So 0.976. So I'm going to fill that in. And it's ATM because it's a pressure for my dry H2. Now notice I have P1 written here. So this is the P1 that I'm going to fill in when I get down here. So I'm trying to fill in these spaces for that combined gas law as I go through here. All right, the next value is the volume of the experimental H2. Okay, so this was when the experiment was conducted, how much gas did they trap? And in the first trial, they trapped 36 milliliters. And what we need to do is convert that into liters. Okay, so to convert to liters, hopefully you wrote this down. I'm going to go ahead and erase it. You can always rewind. It's milliliters to liters, so it's metric to metric. So we're thinking back to that KHD space DCM, King Henry died drinking chocolate milk. What's going to go in the empty space is going to be an L, because we're talking about a volume, liters. We're starting at the little m in milliliters, right, little m, and we're going to move 1, 2, 3 to the left to get to liters. Okay, so I have 36.0. I start at my decimal, and I do the same thing I did up here. 3 times to the left. What's going to go in that empty space? A 0. So I get 0.0360 liters. Okay, so that's the value that I'm going to plug in for my V1 down here. So notice so far I have everything on this side. I have P1, V1, and I have T1. P1, V1, and T1. All right, so the next one. So this one's going to be a little bit more intensive. So I'm going to erase this and give myself some more space. The next one is the experimental volume. So it's similar to the previous, but now we're going to correct it to STP conditions. And if you remember what STP conditions are, they're standard temperature and pressure conditions. So for standard temperature and pressure, we have standard temperature is going to be 273 Kelvin, and standard pressure is going to be 1 ATM. Okay, so I'm going to bring this equation over here, and I'm going to show you how we're going to use it. So P1, V1 over T1. So that's the same as we were looking at before. Think of it as P initial, 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 and then that's equal to the final values, or P2, V2, T2. So how we're using this is over here, the ones, P1, V1, and T1, this is the experimental. And over here, this is going to be at STP. So the experimental values we have, right? P1, V1, T1, it's what they got in the experiment. The STP conditions, we're going to use our knowledge of what STP means to figure out these variables. So experimental volume corrected to STP. So we're solving for V2. We want to know the experimental volume if the standard temperature and pressure were at 273 and 1 ATM. Because you'll notice the experimental conditions, they were at 296 Kelvin. They weren't at 273. The experimental pressure, same thing. It was 0.97. It wasn't exactly at 1. So we're doing this to figure out what would the volume have been if we did it at 273 Kelvin and if we had did it at 1 ATM. Okay, so I'm going to rearrange this equation to solve for V2. Okay, so I want that T2 gone and the P2 gone. I want these on this side of the equation. Okay, so if I multiply by T2, whatever I do to one side, I have to do to the other. So now they're on opposite sides of the horizontal line, so they cross out there. So I have T2, P1, V1 over T1. And on the right side, since the T2's canceled, I have P2 and V2. Okay. Now I still want V2 by itself, so I have to get rid of P2. Since it's in the numerator, I'm going to put it in the denominator. So I'm going to divide by P2 so that they cancel. Since I divided by P2 over here, I'm going to do the same thing over here. So it's going to go in the denominator, P2. That cancels. So if I want to solve for V2, I'm going to take T2, P1, V1 over P2 and T1. All right, well, let me list my variables over here. What are they? Okay, I'm going to put them in orange since I have P1, V1, and T1 in orange over here. So my P1 is 0.976. My V1 in liters is 0.360. My T1 is 296 Kelvin. Okay, well, that takes care of these three variables. But what are my P2 and T2? How do I figure that out? I still need P2 and T2 to solve. Well, we said that this side, the 2's, were at STP conditions, which means they were at standard temperature and pressure conditions. So our values for P2 and T2 are STP. So what's standard pressure? It's just 1 ATM. So that's our P2. What's standard temperature? 273. So that's our T2. So now we have all the variables we need to solve the problem. We're going to plug all of these in and see what our volume would have been if we did do this experiment at standard temperature and pressure. So T2 is 273, P1 0.976, V1 0.0360, running out of room. On the bottom, I'm going to have my P2, which is just 1 because that's the standard pressure. My T1, 296. See, I'm probably running out of room here, so I'll write it up in a second. So 273 times 0.976 times 0.0360. I'm going to divide that whole thing by 1 times 296. So I get 0.0324. 0.0324. Up in markers here. So I'm going to plug in that answer over in my table for the corrected volume at standard temperature and pressure. So 0.0324. 0.0324, and the volume is measured in liters. Okay, so that's how we get this experimental volume corrected to STP. We use the combined gas law, rearrange it to solve for V2, and then our P2 and T2 are standard temperature and pressure values. And the rest of the values we get from the table over here. Okay, so the next one is the theoretical volume at STP. So remember, whenever we say theoretical, that's usually something we calculate. So to figure out the theoretical volume, we are not going to be using any experimental values. Well, I shouldn't say any, because we are going to use magnesium. Let me correct that statement. So for the theoretical volume, we're going to use the ideal gas law. So we're using, PV is equal to nRT. Okay. Well, notice it says at STP, or at least I added that in so that you would know some of these values. So if it's at STP conditions, that means we know two of these variables. So which two variables do we know if it's STP conditions? Standard temperature pressure, so we know temperature and pressure. So our P is 1 atm, our T is 273, our R is that constant, and I hope I'm not getting this wrong because I'm doing it from memory. And it wants us to solve for volume, so this is the guy we're solving for. So we only have one other variable that we need to know, and that's N. So if you remember, N is the amount of moles of something. Okay, well in this reaction, magnesium is the limiting reagent. So if we can take this grams of magnesium and convert it to moles, that will tell us the maximum amount of product that can be made. So off to the side over here, I'll do it in a different color, I'm going to calculate N. So whenever we're calculating moles of something, it's always mass divided by molar mass. Okay? So think of your railroad tracks, right? Well, let me start with the molar mass. So in this case, we're going to use molar mass of magnesium because we're going to take this gram amount, this mass, and change it into moles by dividing it by the molar mass. So the molar mass of magnesium, surprisingly, I don't have that in my head at the moment. Let me find the periodic table. So it's 24.31. So 24.31 grams per mole. Okay. So this is my conversion factor. If I start my railroad tracks, I start with what I know, and what I know is that I use 0.0342 grams of magnesium. I want to get rid of grams, so I'm going to divide by the molar mass, or put the gram portion on the bottom, so that the 1 mole portion goes on top. That way, grams and grams will cancel, and my answer will be in moles. So if I take 0.0342 divided by 24.31, I get 0.0014 and a whole bunch of numbers. So 0.0014,068. And the reason I'm going so far with these numbers is because this isn't a final answer, so I'm not worrying about sig figs. Okay? This is just a number I'm using in the calculation, and the more numbers that I have available to me, the more accurate my answer is going to be. So since this is moles, this is actually my N value. So I'm going to plug that in for my N. So now I know P, I know T because of standard temperature pressure, R is that constant, and then N I calculated by taking the mass of magnesium used in the experiment and dividing it by the molar mass to get moles. So what I'm solving for is V. So let's rearrange this equation to get V by itself. So if I want V by itself, I'm just going to divide both sides by P so that the P cancels. So my equation is going to become volume is equal to nRT over P. So plugging in, my number of moles is 0.0014068. My R is 0.08206, and my temperature is 273. It's cutting off the side there. And then of course my pressure is just 1. So if you can't see that, let me write it a little bit bigger here. Sorry about that. Kind of got away from me there. So we're multiplying all that and dividing it by 1. So Take that times 0.08206 times 273. I get volume is equal to 0.0, how many sig figs are we looking at? Was it 3? Because this one doesn't matter because it's a constant. Those don't matter because they're standard temperature and pressure. So this would be the only one that matters because that's what we use to get moles, so it would be 3 sig figs. Okay, so 0.0315, and units on volume that we're using is liters. So 0.0315. Now if this differed from what I have in the table by that last digit, that's fine, because honestly it depends how far out I went with that molar amount. Okay, or it could depend if I got that R value wrong because I just did that from memory because I don't have my equation sheet handy. So if that differed slightly, I'm sorry, but this is the correct way to do it. I just maybe got the numbers a little different. All right, so almost done. So this is how we get the theoretical volume. Okay, so we have the experimental at STP and we have the theoretical at STP. So percent error is going to be next. So looking at percent error, we've done it a million times in lab. Percent error is always experimental minus theoretical divided by the theoretical. These are absolute value signs, it's always going to be positive, and then times 100 to get it in a percent. Now that experimental and that theoretical, sometimes it's this way and sometimes it's flipped with the theoretical first. It doesn't matter, that's what the absolute value signs are for. It's saying it's going to be positive no matter what, so it doesn't